Welcome to Aksharashala. In this video, I am going to introduce Astable Multivibrator and various types of Astable Multivibrators. And at the end, let us see the operation of collector coupled Astable Multivibrator. Astable Multivibrator, as the name indicates, Astable multivibrator is a multivibrator with no permanent stable states. Both of its states are quasi-stable states only. It cannot remain in any one of its states indefinitely and keeps on oscillating between its two quasi-stable states the moment it is connected to the supply. It remains in each of its two quasi-stable states for only a short interval of time and then goes to the other quasi-stable state. To make transition from one quasi-stable state to another quasi-stable state, it doesn't require any external triggering signal. Here you can see both the coupling elements are capacitors only. Capacitors allows only AC voltage. It blocks DC. So only AC coupling is done from the output of first stage to the input of second stage, and output of AC voltage from the output stage of second stage is coupled to the base of first stage. In the both the AC coupling indicates quasi-stable state, and hence both the states are quasi-stable state. Both the coupling elements are capacitors, no? So hence both the states are quasi-stable states. It is a free-running multivibrator. It generates, if you take output at the collector of second stage, you will get a square wave. It is used as a master oscillator. There are two types of astable multivibrators. First one is collector coupled astable multivibrator. Second one is emitter coupled astable multivibrator. Now let us consider the collector coupled astable multivibrator. This is the circuit diagram of collector coupled astable multivibrator. The collectors of both the transistors Q1 and Q2, are connected to the bases of other transistors. So collector of this transistor is connected to the base of this transistor, and collector of this transistor is connected to the base of Q2 through the coupling elements C2 and C1. Since both are AC couplings, neither transistor can remain permanently at cutoff. No transistor can be at off permanently. Instead, the circuit has two quasi-stable states and it makes periodic transitions between these states. Hence, it is used as a master oscillator. No triggering signal is required for this multivibrator. The component values are selected such that the moment it is connected to the supply. Due to supply transients, one transistor will go into saturation and the other into cutoff. And also due to capacitive couplings, it keeps on oscillating between its two quasi-stable states. See, this is the output of second transistor, which is taken at the collector terminal of second transistor. This is the base potential of second transistor. This is the output taken at first stage, and this is the base potential of first transistor Q1. So if you observe these two, for t less than 0, VC2 at VCC logic 1, but VC1 is at logic 0. So these two outputs are complement to each other. Similarly, if VB1 is positive, VB2 is negative. These two also, these base potentials also complement to each other. Why? Because one transistor will be operated in saturation, other will be in cutoff. That's why the outputs and inputs are complement to each other. Let us say at t equivalent 0, Q2 goes to on state. So here at t equivalent 0, Q2 goes to on state and Q1 goes to off state. So for t less than 0, for this portion, Q2 was off and Q1 was on. Hence for t less than 0, VB2 is base potential of transistor Q2 is negative, and the collector potential of transistor Q2 VC2 is how much? VCC, and base potential of transistor Q1 is VBE SAT, and collector potential of transistor Q1 VC1 is VCE SAT. These are the initial values for t less than 0. Output circuit, heavy current flows in the output circuit, so more drop across RC. Then what happens? Collector potential VC2 decreases. VC2 decreases by this much. VC2 decreases by drop across RC, I2 RC. So VC2 decreases by how much? I2 RC. VC2 decreases by I2 RC, drop across RC. And if you apply KVL in the output loop, I2 RC is given by VCC minus VCE SAT. So VCC minus VCE SAT. This decreases by this much. The drop in, so now collector potential of transistor Q2 decreases by I1 RC. So this decrease in collector potential is in turn connected to the base of transistor Q1. So base potential also decreases by same amount. So this decrease in potential is coupled to the base of transistor Q1 through the coupling element C1. Then what happens? Hence base potential also falls by same amount, that is I2 RC. Here collector potential decreases by I2 RC, no? So base potential of transistor Q1 also decreases by same amount, that is I2 RC. Then what happens? Q1 goes to off state. So the base potential of transistor Q1 decreases by how much? Initially it is at VBE SAT. Now it decreases by I2 RC. Hence VB1 equivalent VBE SAT minus I2 RC. I2 RC. So VB1 equivalent VBE SAT minus I2 RC. And its collector voltage VC1 rises. Now what happens? So it is in off state, no? So no drop across I1 RC. So almost its collector voltage is equivalent to VCC. So its collector voltage immediately increases towards VCC, rises towards VCC. This rise in VC1, now collector potential of transistor Q1 rises towards VCC, no? So this rise in VC1 is again coupled to the base of transistor Q2 through the coupling element C2. So the base of the transistor Q2 also rises by same amount. So the increased amplitude causes an overshoot. So this increased amplitude causes an overshoot. Overshoot means undesired increase in the amplitude, which causes some distortion. So generally we will expect sharp transition, no? But it takes some time, which causes some distortion in the signal. That is called overshoot. This overshoot, so this increase, undesired increase in the amplitude is called overshoot. This undesired increase in amplitude causes an overshoot in the output of transistor Q1 VC1. So and the abrupt rise by the same amount delta in VC1 as shown in figure. Now since Q2 is on, so what happens? This is on, no? So then this is off, this is on. So transistor Q1 starts charging through this path. So it is charging towards VCC through R1 and AND transistor. Then what happens? The potential across capacitor C1 increases exponentially. Hence, so this capacitor voltage is connected to base of transistor Q1, no? So VB1 also rises exponentially. So at T equivalent to capital T1 at this point, at this point at t equivalent to capital T1, when VB1 rises to VB1 rises to, so at this point when VB1 rises to V gamma, Q1 starts conducting. Due to regenerative action, Q1 goes into saturation. In this period, Q1 goes into saturation and Q2 goes into cutoff. Now for T greater than capital T. So this is T greater than capital T. T greater than capital T1. T greater than capital T1. In this period, the coupling capacitor C2. So now it is in off state, no? So then what happens? C2 starts charging. C2 starts charging towards VCC through R2 and on transistor. Q1 is on, Q2 is off. So this through this on transistor, C2 starts charging. C2 starts charging. Then what happens? The base potential of transistor Q2, VB2 you can see. So VB2 also rises exponentially as the capacitor voltage C2. So the coupling capacitor C2 charges from VCC through R2 and on transistor, and at T equivalent to T1 plus T2, when VB2 reaches cut-in voltage V gamma, Q2 again starts conducting, and due to regenerative feedback, Q2 goes to on state. Again in this state, reverse operation, Q2 goes into on state and Q1 goes to off state. Now for T greater than T1 and means this period, T greater than, in this period, capacitor C2 charges from VCC through R2, and at T equivalent to T1 plus T2, when VB2 equivalent to rises to cut-in voltage of then Q2 conducts, and due to regenerative feedback, Q2 goes to on state and Q1 to off state. Just this cycle of events repeated again and again. The cycle of events repeats and the circuit keeps on oscillating between its two quasi-stable states. Hence the output is a square wave. It is called a square wave generator. Square wave is a non-sinusoidal oscillator, no? That's why it is also called as relaxation oscillator or non-sinusoidal oscillator. It is a free running oscillator. So to make transition from one quasi-stable state to another quasi-stable state, it doesn't require any external triggering. For this reason, it is also called as free running. For any queries, please contact aksharshala@gmail.com. Thank you. For further updates, please subscribe to Aksharshala.